So examples 5 through 8, you were asked to solve various systems of equations and to write the solutions, and if the case of special cases, identify them and so forth. So for this one here, not only do you have one equation solved for y, you have both equations solved for y. And because of that, you can actually use substitution, because if y equals x plus 9 and y equals negative 2x, that means that negative 2x has to equal x plus 9. It's still substitution. So you still have an equation that only has one variable. You can solve this. So subtracting x from both sides, and then dividing both sides by negative 3, you get that x equals negative 3. And then going back to one of these two equations, it doesn't matter which one, the bottom one was chosen for this case, and substituting the x value in, you're going to have y equals positive 6. So the solution to this system of equations is negative 3, 6. For the next problem, again, you have one equation already solved for y. So again, substitution is probably a better way to go with this. So using this first equation, I'm going to substitute that in for y down here. So we have 2x minus 3 times the quantity 2/3 x plus 5 equaling 9. Distribute the negative 3, I get 2x minus 15 equals 9. And you simplify this left-hand side, 2x minus 2x cancels. It's leaving you with negative 15 equaling 9. So when one variable was eliminated, either through substitution or elimination, the other one followed suit and got canceled as well. Anytime that happens and you're left with a numeric equation, you do have a special case, and your special cases are either going to be no solution or infinitely many solutions. It all boils down to analyzing this equation. This equation is false. And because this equation is false, that means that there's going to be no solution to this system of equations. In actuality, if you would graph both of these lines, you would see two parallel lines. They would never intersect each other. Now, in this case, it was chosen to eliminate y again. It could have eliminated x's just as easily, but since the y's already had opposite signs, it was chosen to eliminate the y's. So multiply the top, both sides, by 2. You get 16x plus 10y equals 44. The bottom equation stays the same. When you add the two equations together, the y's cancel. You have 20x equaling 35. Divide both sides by 20, and when you simplify that fraction, you get 7/4. Now you're going to substitute this back into one of the two original equations. It doesn't matter which one. I chose the bottom one, so 4 times 7/4 minus 10y equals negative 9. Simplifying the left-hand side, I get 7 minus 10y equals negative 9. I need to subtract 7 from both sides. Then divide both sides by negative 10, and I get that y equals 8/5. So the solution is 7/4, 8/5. I could also do them in decimal form, 2.75, 1.6. It doesn't matter, they're both the same thing. The only time I would usually not recommend doing decimals if you have repeating decimals and you have the tendency to want to round them, it might be better to leave them in fraction form. For this one here, 4x plus 8y equals 40 and 3x plus 6y equals 30. Again, I chose to eliminate, in this case, the x's. So I want to get the same number in front of them but opposite signs. So they're not factors of one another. They don't have a common factor. So I had to try to find a way of getting a common multiple between them. So the top equation, both sides were multiplied by 3. The bottom equation, both sides were multiplied by negative 4. That's going to give me a positive 12x here and a negative 12x here, which would make the x's cancel. That's my goal. As I work out the rest of it, though, I get 12x plus 24y equaling 120. That's what the top equation becomes. The bottom equation becomes negative 12x minus 24y equals negative 120. And so when I add these two equations together, everything cancels on the left, everything cancels on the right. I'm left with 0 equals 0. So again, when I carried through a process to eliminate one variable, both variables got eliminated. They were canceled. And I'm left with a numeric equation. Again, that means I have a special case. It's either going to be no solution or infinitely many solutions. Well, because the situation I have is a true statement this time, it's going to be infinitely many solutions. Now, just because I'm saying there's infinitely many solutions, it doesn't mean that any x and any y paired together is going to be a solution. They have to fit a certain thing. Remember, these are both the same line at this point. So what I'm going to do is figure out, well, what is the equation of that line? Well, one way of expressing it is to solve this for y. So subtract 4x from both sides, divide both sides by 8. And so I have y equals negative 1/2 x plus 5. So sometimes whenever you have infinitely many solutions, you'll see like the solution presented as, well, I have an x value and the y value is going to be negative 1/2 x plus 5. As long as it fits this format, it's a solution to this system of equations. There's just infinitely many of them. It also could have been the case if I take this equation here and solve it for x by subtracting 5 from both sides, multiplying both sides by negative 2. I get negative 2y plus 10. I could also express it like this. Negative 2y plus 10 is the x-coordinate, and then I have a y-coordinate. If it fits this format, it's also a solution. So either way, that's how you would usually express a solution for infinitely many solutions for your ordered pair. So that is the end of this problem, and that is the end of this video. If you have any additional questions, please make sure to bring them up during class.